Not yet, yeah.
Yeah. There is no bigger mic for him.
The mic. No, the mic hold.
I know.
There is one. I mean, just a thing. So, what is happening that most of the people they are standing here and they are looking at the back.
No, I didn't look. Yeah,
We have the screen
yeah,
there.
yeah.
Yeah.
Okay, so how is this?
This is the monitor. You can use it to text something.
Okay.
You can use it in that screen.
Okay.
So we'll look back. I mean,
Yeah,
that is
sure.
maybe you can use.
Okay, so am I audible?
I'll turn on the mic.
Yeah.
Oh, okay.
Start. Maybe you can. Can you start? You think? Maybe couple of minutes. Yeah.
36 seconds.
Yeah.
Check the slides. Forward, backward.
Yeah.
Wait.
Yeah.
And just point something over there.
Yeah.
Working, right? We are talking and we can start something to be able to.
So, this session is just, he works closely with IMC and he also stuff like CMI. Institute of Technology in Mumbai. She's going to exactly give MSTs. So,
Yeah, thank you for the introduction and thank you for the organizers for inviting me here. So this is work on a graph theoretic problem which we tried to tackle using algebraic complexity techniques. So this is joint work with Pratim Datta, who is a PhD student at DICT, Rahul Muthu, who is here, and Sunita. Right. Okay, so this is our problem of interest. Basically, we are given two non-negative integers n and k. We want to know if there is a simple edge-weighted undirected graph with n vertices which have exactly k minimum spanning trees. Okay, right? Okay. So in fact, it turns out that it suffices to find the smallest such graph, the graph having a minimal number of vertices which have exactly k MSTs. Right? This is easy to see. For instance, this is a graph which has 16 MSTs. It is the smallest graph having 16 MSTs. And then if you want to increase the number of vertices without changing the number of MSTs, you can just connect these paths, right? So all those edges have to be part of that MST and then that is fine. Okay. So this is the notation we'll use. We are given this integer k, which is the number of target spanning trees. We'll use alpha k to denote the least integer n, such that there's a simple graph on n vertices, which has k MST. So the lower bounds, so there are some lower bounds known. For instance, you can show that n is at least log k by log, right? Okay. And the proof for this is simple. We know Cayley's formula. Any n vertex graph can have at most n to the power n minus 2 spanning trees. The inverse function of this turns out to be log k by log log k. So we want to get as close to this bound log by log log as much as possible. Okay, so now we want to find matching upper bounds. It turns out that it is enough to find a good enough upper bound for primes. Okay, so let's say there are two positive integers n1 and n2. If we want alpha n1 dot n2 turns out to be subadditive, alpha n1 plus alpha n2 minus 1. The proof for this is simple. Let's say we have two graphs. One of them has n1 MSTs, the other has n2 MSTs. Then we take the single vertex union of these two graphs. And it will turn out that the resulting graph has n1 dot n2 MSTs. Right? So for instance, this is the graph. You find an MST for G1, find an MST for G2. The resultant MST will be an MST for the entire graph. Okay. Right. So we now want to know what are the upper bounds on this alpha of P, where P is a prime. Right. So one obvious upper bound is we take a cycle of length P. It will have P MSTs because all we need to do is delete an edge from this cycle, which breaks it up. Right. And then there are several results. So this is open problem on alpha n, whether it is log n by log log n. So it has been studied since the 1970s, and there were some improvements. The first result on this was that alpha n is at most n plus 6 by 3 if n is 0 mod 3, and n plus 4 by 3 if n is 2 mod 3. Right? So these are some simple results. And then people considered this Fibonacci primes. For this, we can get very close to the log p by log log p bound. In fact, it turns out that we consider this p-fan graph where each vertex is adjacent to. So this is what it looks like. And there was a result which says that this has f2p spanning trees, where f2p is the 2pth Fibonacci number. Okay, right? And we can easily prove by induction that this Fibonacci number is at most O of log p. Right. So we are very close to the log p by log log p bound, but only for a restricted class of Fibonacci prime. Right. But ideally, we want to have an infinite sequence of primes for which this, one vertex which is adjacent to the remaining vertex on the p path. Yeah. But the problem is, as far as I know, it's still an open question whether there are infinitely many Fibonacci primes. We do not know whether there are infinitely many such primes. So ideally, we won't like to have this log p bound for an infinite sequence of primes. Okay. Right. Okay. And what we try to do is we bring in some algebraic complexity. Right. So we know this matrix tree theorem, which says that number n of spanning trees can be represented as the determinant of a small matrix with bounded integer entries. Okay. Right. So we're given an integer n. Now we want to find the smallest dimension matrix such that n is the determinant of that matrix. Okay. Right. So for instance, let's say take some arbitrary number 4, 2, 1, 5. We want a matrix with integer entries between -1 and 10. So this is a simple matrix which does that. You just express the digits in the topmost row. The diagonal entries will have 10 and the subdiagonal entries will have -1. Right. So in fact, this will work over any base. In this case, we are looking at base 10. It turns out that every integer up to k power k, you can look at it as a number in base k, and therefore it can be written as a determinant of a k plus 1 cross k plus 1 matrix with entries between -1 and k. The same idea being used here. Okay, so this is interesting because now using this idea, Rote in fact showed that every integer up to k power k can be written as the number of spanning arborescences. So in the directed setting, at least we can match this bound log m by log log. You can see that there's slightly more number of vertices. That is because here we have those numbers 4 to 1, 5, right? So this will correspond to multiple edges between the same pair of vertices. And that is what we don't want, right? We are looking for simple graphs where there is at most one edge between any pair of vertices. Okay, right? And so the solution to that was that they subdivided certain edges, which can help in maintaining the number of MSTs at the cost of introducing slightly more number of vertices. Okay, so at least for directed graphs, we have an exactly matching upper bound for this. But the real challenge is undirected graphs. So here we are not just looking at some matrix, we want a symmetric matrix with that particular determinant. So can every integer up to k power k can be written as a determinant of this symmetric matrix with those entries. Right? So one idea is this result by Grenet, Kartop, and Korana-Portier, which showed that any n cross n determinant can be transformed into a symmetric determinant of dimensions O of n to the power 5. Okay. So the best we can hope is some log n by log n to the power 5. But it turns out that this is not good enough because of this recent strong result by Strong. He showed that alpha m is log m to the power 3 by 2 by log n for undirected graphs. So somehow we need to beat this bound, right? Okay, so our idea was, okay, we started with any prime p, and if you want the smallest edge weighted graph, what is the maximum number of edge weights you will need? We showed that in fact only weights 1 and 2 will suffice. Okay, and then we looked at, we said, okay, instead of any general graph having that particular number of spanning trees, we look at a restricted class of graphs, and we showed that for that class, that is still powerful enough to show that any integer between 1 to n square, you can have that many spanning trees using only n vertices. Okay, and in fact, this is an existential result. We showed that any geometric range between 1 to n to the power n minus 2 has at least one integer k such that there's an n vertex with exactly k n. Okay, right. So yeah, so the first one is that only weights 1 and 2 will suffice. Okay, right. So the idea is that if you have a graph with k MSTs, it weights in the range 1 to some w max. So we can assume that those edge weights do not have any gaps between them. And this is a standard result which says that at least one minimal weight edge must appear in every MST, and every vertex has at least one incident edge of weight 1. Right. So there are multiple choices. Now, either there's a single connected component with weight 1. Otherwise, if there are more than one connected components, we say that each of the connected components must be a tree. And then using this, we show that weights 1 and 2 will suffice. 0.2? Sorry. Yeah. So
second part of it, every vertex has at least one instance in the weight.
Yeah. Yeah. Every vertex, yeah. So you can take any vertex, you take the minimum weight which is incident to that vertex, and then you can just replace it by 1. Right. So, yeah. Okay. So right, if the subgraph, right. So let's look at the subgraph induced by weight 1. If it is entirely connected, we are fine. Only weight 1 will suffice, and otherwise more than one component of the subgraph introduced by weight 1 is, right? So if there are more than one components, if any of these components has more than one MSTs, let's say D MSTs, then that D must be a divisor of this prime because it must appear in every MST appearing over here. So we cannot have cases like this. It's because if D divides that prime P, then there are only two options, either D equal to 1 or D equal to P. If D equal to P, then we get a smaller graph with P MST. Right? And in fact, we assume that this was actually the smallest graph sitting over here. Otherwise, each component of subgraph induced by weight 1h has exactly one MST. But if that is the case, then we are fine because these components must then be connected by the next smallest weight edge, which is weight 2. If there only one component, again weights 1 and 2 suffice. If there are more than one component, we can use the same idea and show that each of these components has exactly one MST. In fact, each of the components must be a tree over here. But then again, if each of these components is tree, even after linking the weight 2 edges, they will also form a tree, and therefore we can simply replace that 2 by 1 again without affecting the number of MSTs. So in this way, finally, we can use only weights 1 and 2 and get the required number of MSTs. Okay. Yeah, so the second result is here. So for any integer, if you want any number of MSTs between 1 to n square, it is sufficient to look at only n vertex weighted graphs here. Okay. And here again, we split into two cases, composites and primes. For composites, we are able to give an inductive proof. And for primes, we do a case by case analysis depending on the remainder modulo 10. Okay. Right. So these are the candidate graphs which we are looking at. Right. So there are some red edges, blue, green edges, and yellow. So the red edges all have weight 1, the others have all weight 2. Okay. Right. So since the red edges are the edges with the smallest weight, they must appear in every MST. And then we want to use the other edges to connect these two paths together. Right. It is easy to see that there will be at most one yellow edge because two yellow edges might create a cycle. So if a yellow edge is included, then obviously we need to exclude at least one green edge and one blue edge. Otherwise, again, they'll create a cycle. And if no yellow edge is included, then either one green edge or one blue edge should be missing from here. Okay. So let's say, so we are able to count the number of MSTs in terms of the number of yellow, blue, and green edges. It turns out to be B plus G plus YBG. Okay. So the way we look at this expression is, you can think of it as a linear combination of elementary symmetric polynomials. So BG and B plus G. Okay. Right. So this is another kind of graph. Again, we have these red paths. So there are three vertex disjoint red paths, and each of these vertices are connected by a certain green, purple, and blue edges. Right. So all these green, purple, and blue edges are assigned weight 2. Again, all red paths must appear in every MST because they have the smallest weight 1. And here the total number of MSTs turns out to be PG plus GB plus PB, which is again the elementary symmetric polynomial of degree 2 in 3 variables. Okay. And in fact, this is scalable as well. You can have n such paths, and the number of MSTs will turn out to be the elementary symmetric polynomial of degree n minus 1 in n variables. Right. Okay. Right. So the way we approach this is, let's say K is our target number of MSTs. We find integers alpha 1, alpha 2, alpha 3 such that K equal to the element alpha 1, alpha 2 plus alpha 2, alpha 3 plus alpha 1, alpha 3. And then we found some positive integers A, B, C which satisfy these bounds. Right. Finally, it turns out that we can show that there is an explicit graph these many number of MSTs. And in fact, the first step is not difficult because if you want to find such alpha 1, alpha 2, alpha 3, our idea was to add a small square number so that it decomposes into two factors. Right. So you can actually find those easily. Okay. Right. Okay. The proof for composites is a simple inductive argument where we say that, okay, let's say we have some K vertex graph with exactly L MSTs where L is between 1 and K square. And then at K plus 1 step, we need to prove that there's a K plus 1 vertex weighted graph with MSTs at most K plus 1 whole square. Right. So 1 to K square, because we have that K vertex graph, we can just add one more vertex and so that. Otherwise, we'll look at a composite number in this range, K square plus 1, K plus 1 whole square minus 1. Right. Again, it will have at least one factor, which is at least 2 and at most K. It cannot have two factors which are both K plus 1. Right. And so other factor F is at most K square. So there's a K vertex graph with that many number of MSTs. We had one more vertex which shares edges with some subset of these first K vertices. So one of these edges we have to include, and that will correspond to the other factor. Okay. So the only number which is not included here is K plus 1 whole square because it has two factors of K plus 1. So we use the fact that there's a K minus 1 vertex graph with K plus 1 MSTs. Okay. So now there are two vertices which we can add, and we observed that they can have at least K plus 1 neighbors to the first. So the only way you can connect those two vertices are via these edges. Okay. Right. Okay. So yeah. So there's one more result which says that any geometric range. So if we have these target number of MSTs, there cannot be too large a separation between the target number of MSTs using only n vertices. Right? So each of these ranges will have at least one integer such that there's an n vertex graph with exactly k MSTs. Okay, again, it's an inductive argument. Let's say we have an n vertex weighted graph with k MSTs. So the base case is trivial because there are only n MSTs and n vertices, so we can easily compute those. Suppose there is an n vertex graph in where the number of MSTs belongs to this range. We show that the size of the next inductive step is that it is at least as large as k, where k was the original number of MSTs sitting here. Okay. So therefore, there has to be a multiple of k sitting here. And finally, we show that n times the number of MSTs. So this multiple has to be at most n, at most k times n. Is either within or greater than the time range, right? And yeah, there's some open questions which we are interested in. One is infinite family of primes for which the smallest graph has log p n number of vertices. For Fibonacci primes, it obviously holds, but we do not know whether Fibonacci series is an infinite series. And what is the complexity of computing the minimal graph with k MSTs? We do not know whether it's in P or NP complete or yeah. Maybe you could also look at some AC0 lower bounds for this particular question, right? Okay. Even n vertex graph with k MSTs, what can be said about n-1 vertex graph with k MSTs? It appears that there should not be too much of difference between the number of edges in the n vertex graph and number of edges in the n-1 vertex graph, but it would be nice to obtain a good proof for this. Okay, so yeah, so there's some nice references on this topic. So there's a blog by Lipton and certain other papers which we looked at. Okay, okay, then questions.
So any questions before we move on to the next speaker? Let's thank the speaker again. So our next speaker is Prerna Chatterjee, who completed her PhD under Ram Prasad at TFR, and she was then a postdoc at the Czech Academy of Sciences and Tel Aviv University, and was a visiting faculty at NICER Bhubaneswar. And she will be joining IIT Madras next April as an assistant professor.
Yeah, okay. Thank you for to the organizers for giving me the opportunity to talk at such a nice event. And yeah, so this talk is essentially going to be about one of the statements that Ramya mentioned in her talk, which was that there is an almost quadratic lower bound against constant degree polynomials. And since that talk, at least some of you were interested to know why that is true. And this, I just thought, because it's a very nice small proof, and the technique is a bit different from the usual lower bound proofs that happen in algebraic complexity. So I thought I'll just give the full proof of that fact. Okay. Yeah. So because we haven't seen formulas today, let me just recall the definition. Okay, so an algebraic formula is so the underlying graph is a tree, and the leaves are going to be labeled by under the underlying variables, or can be field constants, and the internal nodes are labeled by additions and multiplications. Okay, and therefore you can see that each node naturally computes a polynomial. So the blue things are essentially the polynomials computed at each of the nodes to the left of it. Okay, and we assume that the fan-in is 2, and therefore we can assume that, so usually the size is the total number of nodes in the graph, but because fan-in 2, so we can just assume the size to be the number of leaves. Okay, and as was mentioned yesterday, so Kalarkoti showed that any formula computing the n square variate determinant polynomial requires size n cubed. So because it's n square variate, essentially it's an n to the 3 by 2 lower bound. But his Kalarkoti's technique can essentially be used to prove a quadratic lower bound for the polynomial that is written there. Okay. Right. And again, as was mentioned yesterday, we can basically modify that proof to show that there is an almost quadratic lower bound for any for constant degree polynomials. Okay, so for any k greater than 3, there will exist a degree k polynomial such that any formula computing it must have size n to the 2 minus 1 by k. Okay, and yeah, we'll basically see the proof of it. So to define the measure that is used, as we saw yesterday, algebraic lower bounds, usually you will have a measure and you show that the measure is small for any polynomial that is computed by the model, efficiently by the model, and then you prove that there is some polynomial for which the measure is large. Okay, so to define the measure for the proof here, we need to define this notion of algebraic independence, which is, so suppose you are given a set of polynomials, okay, over n variables. They are said to be algebraically dependent if there is a polynomial which is defined over the same field such that the given polynomial is a root of that. Okay, and if no such annihilator exists, then it is said that that set is said to be algebraically independent. Okay, and so the algebraic rank of a set of polynomials is essentially the size of the largest subset which is algebraically independent. And so now what is the measure? Given the polynomial, what we are going to do is we are going to partition the set of variables into some parts, okay, say k parts, and so for each so for each part, what we are going to do is we are going to write the polynomial as a set, a sum of monomials. So the x to the e's are, so the monomials we are only going to look at in over the variables which are in xi, and everything else is going to be there in the, so the fe is not a field constant, but they are polynomials over variables in all the variables minus xi. Is it clear? So the monomial part is just variables in xi and everything else you pull out. Okay, so we write the polynomial in that form, and so now you have a set of polynomials fe's. Okay, and so this gamma of xi is going to be the algebraic rank of those polynomials, and the measure, so the gamma of f is just going to be the sum of gamma xi's. Okay, is the measure clear? Okay.
Depends on the partition what is.
Yes, yes, yes. Right. Okay. So now what was shown is that if a polynomial is computable by a formula of size s, then that measure is upper bounded by s. Okay, so the what gamma measure is, Kalarkoti's measure is upper bounded by s. Okay, and now once we have that, it's easy to see that that polynomial that was there, which is summation. Okay. Yeah, what is the polynomial? Summation. So you have the y variables and you have x variables. So the x. So note that. So let me show the partition. Yeah. So with this partition, it makes sense, right? So for every I, we'll just take xi to be a single xi. Okay. So now if that polynomial as just a polynomial over say x1, then what it will look like is you have different degrees of x1 there, and everything else is constant. And how many degrees are there? There are n of them. So so basically what you can write is that polynomial can be written as polynomials where x1 doesn't appear and the remaining things. Therefore, the gamma of xi for any I is n, because y1, y2 up to yn all appear as the FEs here, right? And therefore, the measure of the polynomial itself becomes n square, because there are n parts, and for each part the measure was n, right? And as Ramya mentioned yesterday, the point is that if you look at the polynomial one more time, I mean a bit carefully, the individual degree of the polynomial is n here, because individual degree is n. So therefore an n square, and there are n variables, so 2n variables. Therefore an n square lower bound is not, I mean it sort of comes off trivially anyway, but the point is that of course Color-Cotes thing worked for a multilinear polynomial, which was the determinant, but more, I mean what we will see is that this technique also gives non-trivial lower bounds for a constant degree polynomial, which is not something you can do, I mean which doesn't follow trivially essentially. Okay, so we will see the proof of the upper bound a bit later, but let's just see how to it is n, it is equal to n. Because of the, it's probably n, no, it's n only, yes, n only. Okay, so to make it work for the constant degree case, let's just see a proof for the degree 3 case. Okay, so suppose we want to come up with a polynomial which has degree 3 and the lower bound should be something better than, or should look like 2 minus something. Okay, so let's just see what it will look for in the degree 3 case. So what do you think the idea should be? The idea is that here the z variables are going to play the role of the y variable. So we will have n copies of that thing, of that variable, which will give you a gamma xi being equal to n for each I. And essentially what we are doing is just writing the x to the I thing as we write that I in base root n. Okay, so that's essentially all doing. So if you see, so earlier whatever was the base of the y variable is we are writing that in base root n notation, and whatever was xk to the something, that is again getting split over into degree 2, right? And once we do that, we just take the partition which makes most sense, right? And it's easy to, just to check that the number of it. So there are root n parts, and each part has about root n variables. So it is indeed over n variables, and the degree is 3. And if you, by the same logic essentially, for each xi the measure is n, but now this time because you have root n parts, the measure of the polynomial itself is going to be n to the 3 by 2. Okay, and now how do you extend it to any constant? Instead of writing it base root n, you write it as base n to the 1 by c if you want degree c polynomial. Okay, which is what I've done. It just notationally heavy, but same idea. But because you need the total number of variables to be n itself, what you will see is that the number of parts you can accommodate is n to the 1 minus 1 by c. Okay, and same idea of how you take the partition, and number of variables stays some constant times n. Here d is constant, And but because the number of parts is now n to the 1 minus 1 by d, what you get is a n to the 2 minus 1 by d lower bound instead of n square. Okay. Right. So now this was the easy part. So the more interesting part is really the upper bounding of the measure, right? So if you have a polynomial which is computable by a formula of size s, then the algebraic rank or the sum of algebraic ranks depending on the partition is at most s. Okay, so this is essentially the algebraic analog of Nechi-Poruk's proof of the n square by log n lower bound in the Boolean setting. Okay, which is why, yeah, this sort of comes in. Anyway, so let's see the proof of the upper bound. So suppose you are given a formula of size x which computes your polynomial. What you want to do is you divide up the leaves of the formula into so the LXIV is going to be, so given any vertex in the tree, then the number of leaves under in that subtree rooted at V that whose labels are variables in Xi. Okay? That is what LXIV is. Okay, set of leaves in the subtree of T, which is rooted at V, that are labeled by variables in Xi. And what we will show is that gamma Xi of F is at most the number of leaves like that. Okay, when you think of the full. And this, if we can do that, what we have is gamma of F is some summation I gamma XIF, and again sum of that will be all the leaves, okay, which will give. Okay, so now how do we prove that? So we just fix some Xi, and the main idea is that you want to, so given that formula T, you want to modify that into another formula where now the leaves are no longer just allowed to be variable, I mean labeled by variables, but they can be labeled by polynomials as long as the variables on which that polynomial depends only come from variables outside of y. Okay, so for free you're allowed to compute polynomials over variables that you are not interested in. Okay, and but the y variables should stay as is, so that the number of leaves, the number of y leaves in the new formula also doesn't change. Okay, so, and of course it should compute the same polynomial. So the new formula should compute the same polynomial. The number of y leaves shouldn't change. You want to keep that untouched. Yeah, and additionally what you want is that the total number of leaves now in the new formula is upper bounded by the number of leaves. What have I written? How is upper bounded by L? Fine. That is, yes. Okay, yeah. Total number of leaves should be upper bounded by just the number of leaves in Y itself. Okay. So the number of leaves which are labeled by variables in Y, the total number of leaves should be upper bounded by that. That's what we want. Once we have that, then okay. So now, so this is what we want to do. Okay. And also, why? Okay, now if we have this, why are we done? Because now suppose if you write your polynomial as summation fi mi, where mi are monomials only over y and fi's are polynomials outside of that, then because the new tree ty is also computing the same f, by induction you can show that all the fi's are just some polynomial combination of the leaves in this tree, right? So now because of that, what you have is that what is that? So every fi is some polynomial combination of the leaves. So the algebraic rank of that polynomial must, so the algebraic rank of, it should be algebraic rank of all the fi's. That should be bounded by the number of leaves in the tree, right? And because the number of leaves is upper bounded by just the number of y leaves in the in that tree, and the number of that ty is same as the number of y leaves in T itself, what you get is that will give you the upper bound that you were looking for. Okay, because after that you are just going to sum over all the i's and okay. So sorry, right. So what we are going to do now is basically to construct a ty which has the properties that we were looking for. So suppose you have a formula of size s that computes size s that computes f. What we'll do is we'll divide these vertices into some 3 parts. Okay, so V0 are those vertices for which are essentially the subtree under that vertex. They don't that subtree doesn't depend on any y variables at all. Okay, so there can be like chains of that, but we will just look at the topmost one. Okay, so and then V1 is going to be those which those vertices whose subtrees have only one y variable. Okay, again can be chain, but we'll look at the topmost one. Okay? And V2 are going to be those which have multiple or more than one y variables. Okay. So now, because we are allowed computation over non-y variable polynomials for free, any vertex in V0 can basically just be, or that entire subtree can just be replaced by a leaf which is labeled by the polynomial because yv plus 0 the f 0 don't depend on y variables. Oh. Okay. So what were we doing? We were looking at these, we were dividing those vertices into three parts. One where vertices whose subtree did not depend on y variables, one whose subtree had depended on y variable but had only one y variable, and those which had more than one y variables. So those for the vertices in V0, because the entire subtree was computing a polynomial which didn't depend on y, you could, and we were allowing free computation for polynomials not depending on y, we can just replace the entire subtree by a leaf, which is labeled by the polynomial that it was computing. And for those which had depended on only one y variable, it is easy to see that you can write that polynomial as an f1 y plus f0, okay, where f1 and f0 didn't depend on y variables. Okay, so now what are you going to do? You are going to replace that entire subtree by just a gadget which looks like that. So there are like three leaves essentially. One which is labeled by f1, one which is labeled by f0, and the y variable. Okay, and so now because of this, because each v1 variable is essentially just has one y variable that is there, the number of v1 vertices must be upper bounded by the number of y variables in the tree. Okay, and so for v2 also we want to do something similar. We can't immediately do it because what can happen is that there might be these chains of vertices which essentially so there is something on which, I mean, so this v has y variables here, okay, but the uncles that come out, they don't have any y variables. So what you can have is that there are these long chains, say u and v, where the set of y variables on which the polynomial on u depends is the same as the set of y leaves on which the polynomial defined at v depends. Okay, so the y variable set or the leaves where leaves labeled by y's for u and v are the same. This thing can happen. Okay, so what you want to do is you want to get rid of or you want to collapse these things in some. And the way you do that is again very similarly to the the case where there is only one y variable. What you can do now, what you can see now is that the polynomial gu, so the polynomial computed at u, can be written as f1 gv. So instead of now a single y variable, what you will have is that the polynomial computed at v will be there, but you can write it as gu times f1 gv plus f0, where f1 and f0 don't depend on y variables and gv is the polynomial computed at v. And now because of that, what you can do is again, you replace that entire chain by a gadget, right? Same gadget. I mean, this 2 new leaves maybe, and the rest of it being the subtree at v. Okay, so now again, because of this, what we get is that if you have distinct if you have distinct vertices that you took from the set V2, then the set of y leaves for u and the set of y leaves for v must be distinct, because if they were same, we have collapsed them in some. Okay, so now because of that, what you get is that for every vertex in V2, you have some y leaf which is going to which is going to be, you know, like which is going to mark of a vertex in V2, in the sense that there is, forgetting the word, but anyway, I wanted to say something, not, but you, so for so have a distinct y label which this vertex is mine. Okay, so because of that, the number of V2 vertices is going to be upper bounded by the number of y leaves in the tree as well. Okay. So we've upper bounded both V1 and V2 vertices in the tree by in terms of the number of leaves of Y leaves in the tree. Okay. Now once we have that, we have sort of we are done. We are happy. Why? Because we never changed any computation. So the polynomial being computed at the root stays the same, right? And we have also not touched any of the Y leaves as such, right? We have collapsed vertices which don't compute polynomials over the Y variables, but the Y leaves have stayed untouched. So that the number of Y leaves is the same. And both V1 and V2 have now been upper bounded by the number of Y leaves. And now note that everything else has really been collapsed in some way, right? So the number of leaves in the tree itself is upper bounded by either V1 type leaves, V1 type vertices or V2 type vertices. But the V1 and V2 themselves might have at most 3 leaves attached to it because of that gadget that we were replacing them by. So the number of leaves is upper bounded by 3 times the sum of them. Okay, and because that is because those have been upper bounded, so the number of leaves is also upper bounded in terms of the number of Y leaves in the tree. Okay, and now because of that, our proof is done. Okay, and I've finished. Okay, not okay, but so what did we see? We essentially saw that the full proof of the fact that any formula computing this polynomial requires size n square, and although that can be seen sort of trivially because of individual degree being high, what this proof technique does give is that even what it does give is an almost quadratic lower bound against constant degree polynomials. And surprisingly, like the fact that this sort of follows quite immediately from Color-Cotes proof, which has been known for ages. Surprisingly, if you could make that lower bound from 2 minus epsilon to 2 plus epsilon, okay, for constant degree polynomials against formulas against border in the border sense, in the sense, I mean, so if you know what it means, then that's okay. Otherwise, it's formulas where you are allowed to approximate polynomials instead of computing them exactly. Okay, so in a slightly more general sense, but yeah, but if you give slightly super quadratic lower bounds against formulas in a slightly more general sense, what it does give is it gives sub-exponential PITs for linear circuits, okay, which would be like very nice thing to have, okay. And the fact that we can do the 2 minus epsilon so easily, it would be really nice to maybe improve it to quadratic first and then try to make it better than that. Okay, yeah, that's sorry.
Linear side.
Linear side. Sorry. Yes. Oh, yeah. Typo. Not.
If the lower bound is in the border sense, does that imply the normal lower bound, or is there any implication either way?
Yeah. So the lower bound against in the border sense would imply lower bound in the general sense. So this is an easier question, but again, if like all the natural measures will anyway extend to border, which is why maybe it's not but if it's an unnatural measure, then even if you prove it for general, you might have to do more work to prove this. Degree 2, like in what? Like what do you want? Oh, this is for degree 2. Algebraic, I don't think so. I think I had, yeah, I don't think it is. Yes, this one is not. This is one of the few ones which are not actually natural. This algebraic rank thing, which is what I meant when I said that it's different from the usual thing. But yeah, so Bauer-Strassen, the original proof is not natural, but there is a natural. The Smolensky's proof is a natural measure which gives the same lower bound. This one actually, I don't think we know any natural. Yeah, the constant thing. Yeah. Was the degree 2 you said? I don't know. So degree 2 degree 2 polynomials, do you have anything n to the 1 plus epsilon? Yeah, because yeah, these are all like you just make base. Yeah, you do like D Kronecker or something. So I don't know.
So any more questions? So let's thank the speaker. So our next speaker is Jakob Nordstrom, who is at the University of Copenhagen, and he's going to talk about